Right, so today's topic will be on hyperbolic functions. Hyperbolic functions is really not a new function. So the most important two functions will be the hyperbolic sine x and the hyperbolic cosine x. Okay, I probably cannot cover all the other functions, their definition, the derivative, and the inverse, and the derivative of the inverse function. Maybe the derivative inverse function would be the next topic. Oh no, it's covered here as the derivative of the inverse function. So let me focus on the hyperbolic sine x cosine the relationship. Okay, first, it's similar to sine x cosine x. All the formulas we're going to get are very similar, but it's slightly different. Okay, hyperbolic sine x by definition is going to be this function, okay? And then hyperbolic cosine x will be e to the x plus e to the negative x. The most important equation between them is going to be hyperbolic cosine x let's see. Hyperbolic cosine square x minus hyperbolic sine square x is going to be, I think it's going to be 1. Okay, so that's minus. It's easy to verify. You just need to square it, and then lots of terms will be cancelled out, and so you will get 1. Okay, so we also consider the hyperbolic tangent x. Hyperbolic tangent x is a quotient of that, and hyperbolic cotangent x. Hyperbolic cotangent x is going to be hyperbolic cosine x of hyperbolic sine x. All right, so those are the then the secant x, cosecant, hyperbolic cosecant x, and also defined in the same way. Okay, and hyperbolic cosecant x is going to be 1 over hyperbolic cosine x. All right, so those are the definitions. I think the most important one is this and that. Okay, and first of all, let's study the graph. Y equals hyperbolic sine x. Okay, this is defined by that, and clearly it's other function. It is other function when x equals 0 and it's going to be 0. So the graph when x getting large, the second term is actually going to be almost 0. Okay, so it will be very close to. Now let me draw. Yeah, so this is going to be something like it's increasing function, and when x sufficient large, this is almost equal to half of e to the x. So this will be it will be very close to y equals half of e to the x. Okay, the reason is the second term is almost equal to 0. Right, so you can see that, and the other side in a similar way. So it's the increasing function. Then the inverse exists. Okay, so the inverse exists. The inverse exists, and so if you solve for, look at this equation, right? And if you solve for x in terms of y, you get x equals right? X going to be the inverse hyperbolic sine x. Maybe we can call it arc hyperbolic sine. That is going to be right. So I'm very curious about this inverse function. Since the original function is given by by the exponential function, right? Defined by its own. So maybe the inverse function can have another, elementary formula for that. So yeah, if you interchange the variable, you get the standard, yeah, inverse function hyperbolic sine x. All right, how do you sketch the graph? I think the graph will be the inverse function is just located about the midline y equals x. Okay, we can talk about this later. So let's try to solve this equation, right? Let's try to find the inverse, another formula for the inverse function. So the idea is y equals half of e to the x minus e to the negative. Can I solve for x? Okay. I can multiply both sides by 2. And the e to the negative x is actually 1 e to the x, right? So that's good. All right. So how can I solve this equation? This actually becomes a quadratic equation. You multiply both sides by e to the x. Right. So you get it. All right. So you will get e to the x minus 2y e to the x minus 1 equals 0. So this is a quadratic equation in e to the x. All right. Then you can solve for e to the x. 2a negative b plus minus b squared minus 4ac. Right? So minus 4 times negative 1. So you take 2 out, you get y squared plus 1 divided by 2, and then simply you get y squared plus 1. All right, the problem is you cannot take a negative sign, because if it's a negative sign, this would be negative. So you must take, yeah, e to the x must be this, okay? The reason is since e to the x is a positive, okay? Because if it's put a negative sign, it's guaranteed to be negative, the difference, okay? So you take this, then you solve for x. So that is the hyperbolic, the inverse of hyperbolic sine x. Great. You can express the inverse function using elementary function. It's pretty complicated function, but you get it, this function. Right? So once you get hyperbolic, this is defined for all the value for y, right? The domain. So you can find, you can even find the derivative, okay, of the inverse function. Okay. Now, for exercise, I'm going to get, yeah, let's look at the hyperbolic sine x, okay. So you get, yeah, anyway, so you get hyperbolic inverse of sine x is going to be natural log of x if we switch the variable. Okay. So x is defined for any, the function is defined for any x, no restriction on the y value, because you look at the graph, look at the graph, right? Look at this graph. X is defined for as a function that for all x, the value will be from negative infinity to positive infinity. So if we reverse the, yeah, this is x, this is a y, and x is going to be hyperbolic sine x, and here is just a y, right? No. X is a bit hyperbolic inverse of our sine x. y is going to be hyperbolic sine x. Yeah, forward. Okay, so there's no restriction y. Y is from negative infinity to positive infinity. Right? Yes. All right. So this is a graph. This is a yeah. So the domain, you know, the range and domain will be the same for the whole line. So no restriction. So let's take a look at hyperbolic cosine x. Hyperbolic cosine x is not going to be increasing function or decreasing function all along the whole line. It is an odd even function. It's going to be like that. It looks like a parabola, okay, but it's not a really parabola. Okay, it's going to be here when x equals 0, it's a 1. Okay, so this is a parabola. This is a exponential function. So this one is very close to that exponential function when x is sufficiently large. Okay, here's another one, and this is a y equals half of e to the negative x. Okay, so on each side, why they look similar when x sufficient large is because when x sufficient large, e to the negative x is almost 0. Okay, so you cannot define the inverse function. So you have to restrict it to x. Yeah, you have to restrict to x greater than or equal to 0. Otherwise, you're not able to find the inverse function, right? So this is a yeah. Let's see. Yeah, so we assume and clearly we have to assume that x should be greater than or equal to 0. Then that piece, yeah. Let me reschedule the graph. In order to find the inverse, you have to restrict the function to that. X greater than or equal to 0. So x greater than 0, then y is greater than 1, right? Clear. You know, the domain so for range for this function is y greater than or equal to 1. So how can you solve for y? You can solve, yeah, I can solve for x in terms of y, and you can by similar argument, okay? By similar argument, you can find, you can solve for x in terms of y, okay? So these two are equivalent, right? Next to it. So this is the hyperbolic, the inverse function hyperbolic y, okay? So just solve the quadratic equation, you will get this expression. So clearly from this expression, y cannot be less than 1, right? Y squared cannot be less than 1, so y greater than or equal to 1. I'm not surprised. So if you exchange the variable, you will get the graph for the inverse function. So how can you sketch the graph? You draw the line, okay, and this will be the graph. It's a symmetric, okay. So this will be the graph. Y equals hyperbolic, the inverse of hyperbolic cosine x. Okay. And this is the line y equals x. Okay. So we find the inverse, then we want to find the derivatives. Well, one more function. Okay. For the hyperbolic tangent x. Okay. The hyperbolic tangent x is kind of strange function, right? This is a defined because it's by definition it is hyperbolic sine x divided by hyperbolic cosine. Now after simplifying, right, and then clearly when x approaches infinity, this approaches 1. So the graph will be the graph of this function has 2 horizontal asymptotes. Okay, so one is y equals -1, other one is y equals positive. So the graph looks like that. Okay, it's increasing, but and it has a horizontal asymptote. Okay, why it has horizontal asymptote? Because when you look at the limit, as x approaches positive infinity, you will see that the limit is going to be 1, clearly. Okay, why? Because this e to the negative x is almost 0. You can ignore it. E to the x over e to the x, the quotient approaches 1. Okay, so that's why it's going to be 1. Right, so this is a graph. The inverse exists. I'm very curious to find the inverse. How to do that? Okay, it looks like it looks pretty complicated here, right? So we try to solve for x. Okay, so questions: what are we able to express the inverse function by elementary function? We can. Okay, so look at the above identity, right? So you multiply both sides. By the denominator. Okay, so from here, again, you multiply both sides by e to the x. This is square plus y, right? Yeah, then e to the x squared minus 1. Well, in this particular case, you don't need to solve quadratic equation. You move this to the right hand side, maybe. Y is greater than equal to y is between 1 and -1. See the y value. Look at the y value. Y value is going to be between negative and the positive one, right? So I'm going to express in this form. Okay. So e to the x squared. If we write in the more standard form, one is first, right? And then you take the square root. Then you find x. Okay, but then you also can take this out. All right, so this is it's interesting. This is a inverse function. Okay, half of natural log 1 plus y 1 times. It's good. All right, so if you want to find the derivative of a hyperbolic, is the inverse of hyperbolic sine y, you can differentiate this function directly. Okay, it's much easier. Okay. So how do we find the derivative of these functions? So we will only consider hyperbolic sine x and hyperbolic cosine tangent x. Okay, because then maybe hyperbolic cosine x, yes. So let's take a look at, let's try to find the derivative. There are 2 options, right? So here's the question. What is the derivative of hyperbolic sine x with respect to x? You have 2 options. One is use a formula for the inverse function and differentiate directly. Okay, the method 1. Okay. So let's try this. So this is going to be the derivative by the formula. We have a natural log of x plus, right? If you differentiate, so you have to use a chain rule. It's complicated, but it works, right? So you can get x plus this. Then you have the differential inside 1 plus, I think, yeah, write down this. Can you see that? When you differentiate the square root of x squared plus 1, you will get x over square root x squared plus 1. Okay, the idea is when you differentiate x squared plus 1 to the 1/2, you have 1/2 x squared plus 1 negative 1/2 times 2x. After you simplify, you get that. Right, are we able to simplify it further? I think so. And I find that this is cancelled out. You only get x squared plus 1. Wonderful. So that's our motivation to find the hyperbolic, the inverse of hyperbolic sine x, because its integral right now, 1 plus x squared dx is going to be this, right? Recall that. Recall the integral of this, right? This is going to be the hyperbolic, no, the inverse of sine x, okay, which is from the last section. Yeah. So very similar. The only difference is here is a plus x squared and here minus x squared. Okay. This is the reason why we have to introduce the so-called the inverse of hyperbolic sine. Is there any better way to find as a derivative of the inverse of hyperbolic sine x? We can. Okay, the derivative according to the definition, according to the formula, this is going to be the derivative of this function, right? So we have to find the derivative of hyperbolic sine. Hyperbolic sine x, the derivative is going to be hyperbolic cosine. Right. Yeah, there are some formulas for the derivatives: hyperbolic sine x, hyperbolic cosine, hyperbolic tangent x. Hyperbolic tangent x is going to be, yeah, it's very similar. There's some difference, like a derivative of hyperbolic cosine x is going to be hyperbolic sine x, not negative hyperbolic sine x. But for regular cosine x, the derivative of cosine x is going to be negative sine x, right? So there's be careful about this, about their signs. All right, now for this one, what I'm going to do with it, okay? It can be also simplified. Okay, the reason is cosine square, hyperbolic cosine y square minus hyperbolic, I'm sorry, goes to what? Okay, this is identity. So if this considers y, right? So that means hyperbolic of this is going to be square root of 1 plus okay. And why I have to choose a positive? Because usually have plus minus sign, because cosine, hyperbolic cosine is always positive. All right, so this is nothing but x squared. Right? Because hyperbolic sine x meets inverse of sine x is going to be just x. And then square. Okay, so that's another quick way to find the derivative. Okay, so then yeah, this is the denominator, okay? So you can have a quick answer for that. Right, so cool. And then by similar argument, right, you can show that we also have there was a formula in the book, yes. Right. So we have the following formulas. It is going to be right, and here x is going to be greater than 0, greater than 1. Right. That's a restriction on this. You can from formula you can tell that. Right. And tangent, the derivative of hyperbolic tangent x is going to be 1 minus x squared. Now here, x is between 1, okay? Otherwise, the hyperbolic, the inverse of doesn't, yeah, it's not defined. This is defined for x between negative and positive 1. So those are the important formulas. And so let's see. How do we evaluate the integral of this, right? How do we evaluate the integral of this? Suppose you forget all the formulas, right? And this is what you're given here, right? Okay. Now, if we use a formula, let's say, write down what do we get? This is a hyperbolic. This is hyperbolic, okay? Hyperbolic tangent x plus what? Plus c. But the hyperbolic, the inverse hyperbolic tangent x is going to be this. Right? So the integral of 1 over 1 minus x squared is going to be this. Okay, we assume that here the absolute x is smaller than 1. Right? Under that assumption. Under that assumption. If x is greater than 1, maybe not true. Okay. So we have to assume that because we have to go through the hyperbolic, inverse hyperbolic tangent x. Okay. But I can solve the problem directly. How do you do that? This is going to be 1 minus x times 1 plus x, right? So I can separate it. And when I add them together, this product in the denominator. The numerator will 1 plus x plus 1 minus x. X will be canceled out. I think I have to divide by 2, otherwise it's not going to be identical. Okay. Yeah, this is a standard decomposition. Once you know that, then well, you can also change the the order, right? 1 over 1 plus x is here minus I'm changing the order of x. Okay, so this is the same. Okay, we know that the integral of 1 plus x plus any k is going to be absolute natural log of absolute value of x plus k plus constant. That's obvious, right? Right? You can use substitution to find this. Yeah, we did that before. So using this, then you can right? It's going to be, don't forget the x. Okay. So the first term I get is natural log of absolute of x plus 1. The second one is natural log of absolute of x minus 1. And plus constant. Then I put them together. Right. So we get, do we get the same answer almost? Just we have a more We have a absolute value symbol on that. That's the only difference. Okay, that is the only difference. Compare with the one we got here. Okay, and compare with this. The only difference is there is absolute value, but there's no restriction. On here, just x is not going to be 1, x squared. Okay. Why there's always there's a half here. Here there's a half here. Here, this is 1/2. It's a part of that. Yeah. Okay. So this is the reason I divide by 1/2 is because this identity. Decompose. Yeah, you have to divide 2, otherwise this is numerator. If you combine those two terms, the numerator will be 2, okay, over 1 minus x times 1 plus x. All right, so this actually looks like the second method is better. The reason is it holds for x not absolute of x not equal to 1. Okay, it can go beyond the interval. Yeah. Okay, so this is not necessary. As long as it's not going to be 1, that's fine. But if you go through if you go through the inverse of hyperbolic tangent x, then you have to say that x is absolute x is less than 1. Right? So this is a good example. So when you see 1 over 1 minus x squared, you can solve the problem directly without using the inverse of hyperbolic tangent x, or you can write down the inverse of hyperbolic tangent x immediately and without saying, this is okay. But if you still remember another formula for the inverse of hyperbolic tangent x, then you can also put the 1/2 times natural log of 1 plus x over 1 minus x. All right, so those are the those are the interesting formulas. Now, what do we have to do next? Yeah. Okay, so let me record this formula, right? Now, if both sides divided by, if I divided by hyperbolic cosine x, what I get? 1 minus. And that is going to be 1 over hyperbolic cosine x. That will be hyperbolic tangent x. So this is a formula, okay? That tells you the relationship among those quantities. Okay. Yeah. Hyperbolic, okay, is in the opposite direction of the spheric. Okay. In geometry, when we say curvature equals 1, we will get a sphere. Okay, it's curved around, but hyperbolic surface has a negative curvature. Okay, so so this hyperbolic, this word shows up everywhere. So it's quite different. So sine, cosine is like the positive side, and hyperbolic sine, hyperbolic cosine is like, it's on the negative side. Okay, so here its difference is going to be 1, not the sum of them. Okay, sine cosine squared plus sine squared equals 1. Now here, hyperbolic cosine squared minus hyperbolic sine squared is going to be 1. Okay, all right. So let's, in order to understand those functions, let's do some exercise. Right. So if hyperbolic tangent x is going to be 12 over 13, right, find the hyperbolic cosine x and hyperbolic sine x. Well, if you get one of them, then you can get others, right? You can say I can even find x, right? So what is x? X is going to be the inverse hyperbolic of this, right? And we already know the formula. That's going to be half of natural log. That's 1 plus 12 over 13, 1 minus 12 over 13. So when you simplify, you will get natural log of this is going to be 13, yeah, 25, right? And that is going to be natural log of square 25, just natural log of 5. Yeah, okay, that is x value. And why? I'm trying to show you 2 different ways to solve the problem. Okay, then hyperbolic cosine x is nothing but e to the x minus plus e to the negative x, right? So that's going to be e to the natural log of 5, you know, for the value, yeah, and then plus e to the negative natural log. So I can get, the first one is just 5. The second one is going to be 1 over 5. The reason is e to the natural log of 5 is going to be e to the log to the negative 5. So that's going to 5 too, right? Yeah. All right. So you will get 5. 25 plus 1, 26. Divided by 2. So it's going to be 13 over 5. Right? And similarly, you will get, by similar argument, hyperbolic sine x is going to be e to the x minus e to the negative x over 2. So that will be 5 minus negative 5 divided by 2. And that will be 24 over 5 divided by 2. That will be 12 over 5. Okay. Is there any other way we can do that? Yes, I have another more direct way to do it. That this one, I know I find the value of x first, then use the definition of hyperbolic sine x and hyperbolic cosine x. I get the values. Okay, but I also can use the formula when that's the second method. I also can use a formula, and this is going to be hyperbolic cosine x, right? So 1 minus and 12 or 13 square. That is going to be this. Yeah, keep in mind, we have a special triangle here. If this is going to be 5, that's going to be 12, that's 13. Okay? Yeah, that's a special triangle. 12 square plus 5 square equals 13 square. All right, so that's the reason you get 13 square minus 12 square. Okay? Then that's become 5 square in the numerator. So 5 square over 13 square. Okay? Then hyperbolic cosine x is going to be 13 square over 5 square. Since hyperbolic cosine x is going to be positive, so this is going to be positive, 13 over 5. Now, once you get this, you can get it the other way, because hyperbolic sine x is going to be hyperbolic tangent x times hyperbolic cosine x. So that's why it's 12 of 13 times 13 over 5. That's going to be 12 over 5. Okay. So there are many ways to get the same answer. Okay. Yeah, let me, I probably skip that part, let me repeat, yeah, the formula. It's going to be hyperbolic cosine x. When you differentiate hyperbolic cosine x, you get hyperbolic sine x. It's different. This part is different from a trigonometric function. And the derivative hyperbolic tangent x, and the rest of them you can find the formula right in the book. So I'm only list of those three because I'm more interested in this. I'm trying not to make any problems using other functions on the test and quizzes. For yeah, so let's look at the following problem. Right, g of t equals hyperbolic sine lt. Find the derivative. All right, so find the derivative, according to the above formulas, right? It's going to be derivative of a hyperbolic sine x becomes cosine natural log of t, and the derivative of natural log of t is 1 over t, right? Can we simplify now? Well, when you start to simplify, you will realize that probably you can simplify the function first before you differentiate. So your answer is, this could be the answer, okay? That's okay. But if you simplify this, is going to be e to the natural log of t plus e to the negative natural log of t, right? So the first term will be t. The second term will be 1 over t. Okay? So after simplifying, it will be t squared over t, that's 2t squared. This is a derivative. Right? Yeah, again, e to the natural log of t is going to be e to the natural log of t to the negative 1. That's going to be 2 to the negative 1. So that's 1 over t. But I also can simplify at the very beginning. Right? So actually I get t minus 1 over t. So if I combine them, it's t squared minus 1. Or I can write in this form, right? Then it's better. You don't need to use a quotient rule to find the derivative. You just need to take half minus x plus, right? That's the answer. That's quick. Of course, you can write it in this form, no problem. So it's better to simplify the function before you find the derivative. Okay, let's take a look at the next one. Evaluate the integral of this. All right. Well, we have to use a substitution to simplify. So the natural substitution is the square of x. So du equals this, right? So the integral is going to be sine hyperbolic sine u, and the dx over square x is actually 2du, okay? Hyperbolic sine u is going to be the antiderivative of hyperbolic cosine u, and the plus constant. So u is going to be square x, that's constant c. All right. So that's let's look at another problem. Yeah, evaluate integral, definite integral from 4 to 6 t squared minus sine dt. All right, so we have to, when you see that, you have to look at the back, you know, if we forgot the formulas, then, yeah, you find some formulas in the book, the derivatives, right? Which one gives this? I think, yeah, we have to recall the formula. Okay, so this is the formula. Okay, how can I use this formula to solve the problem? It's x squared minus 1 here, t squared minus 9. So I have to introduce, let t to be 3u, okay? Yeah, so dt equals 3 du, and the integral becomes 3u squared minus 9, and dt is 3 du. Now for the new variable, when t equals 4, u is 4 over 3. When t equals 6, u is 6 over 3. All right? So finally, the denominator, I can get, I can take 3 out. So actually it's nothing, just equal to u squared minus 1 here, right? The 3 is gone. All right, then you can say the antiderivative is arc cosine and evaluate at the 2 endpoints. Right. And that will be 2. So this is the exact value. You cannot simplify it further. That's okay. You know, this is yeah, this is answer. Right?